In this lecture, we'll discuss the effects of a catalyst on a reaction by examining the changes the catalyst make on the reaction pathway, how to identify the catalyst in a reaction mechanism, and what catalysts look like in some common catalyzed reactions. In an uncatalyzed reaction, shown here as the red curve, we see a one-step reaction as evidenced by the single energy peak along the reaction pathway. This has a pretty high activation energy, E sub A. If we compare it to the second curve in blue, we see the catalyzed reaction follows a different two-step mechanism, as indicated by the presence of two peaks with an overall lower activation energy barrier. From our studies of the Arrhenius equation, we know that a lower activation energy barrier leads to a faster rate overall. For this reason, a catalyzed reaction will proceed at a faster rate than its uncatalyzed version. Let's consider the uncatalyzed reaction of ozone and atomic oxygen, shown here in blue, which follows a high-energy single-step mechanism to make 2 moles of molecular oxygen, O2. High in the atmosphere, we find atomic chlorine, Cl gas, which is liberated from chlorofluorocarbons. Atomic chlorine can act as a catalyst in the decomposition of ozone, O3, as shown by the red pathway here, step 1 and step 2. In the first step, atomic chlorine gas reacts with ozone to form chlorine monoxide, ClO gas, and diatomic oxygen, O2 gas. In the second step, the ClO reacts with atomic oxygen to regenerate the atomic chlorine and a second mole of O2. This net or overall reaction is the same result as for the uncatalyzed reaction, but we see the rate of ozone decomposition proceeds much more quickly because the activation energy barriers in the catalyzed two-step mechanism are much lower than in the uncatalyzed reaction. We also see that catalysts are not consumed overall in a reaction. This means that, although they react in an early step of the mechanism, they are regenerated in subsequent or later steps. It's important not to confuse catalyst with reaction intermediates in a reaction mechanism. While catalysts are not consumed overall, we see reaction intermediates are formed in an early step and consumed in subsequent or later steps. Either way, the result is the same. Neither the reaction intermediates nor the catalyst show up in the overall reaction. The catalytic decomposition of ozone is an example of a homogeneous catalysis, meaning that the reactants and catalyst are in the same phase. Atomic chlorine is present in the gas phase as it reacts with gas phase ozone and atomic oxygen. In contrast, the catalytic converters in our car's exhaust systems is an example of a heterogeneous catalyst. In this example, we see that harmful pollutant gases, such as uncombusted hydrocarbons, NOx gases responsible for smog, and toxic carbon monoxide, enter the device, pass over a reduction catalyst and an oxidation catalyst, both of which are held on a solid support. The final result is a mixture of relatively unreactive nitrogen gas, water vapor, and carbon dioxide. Heterogeneous catalysts are sometimes tricky to understand, so let's take a closer look at the mechanism responsible for the catalytic hydrogenation of ethylene to form ethane. First, we see hydrogen gas can be adsorbed onto the solid nickel surface, which causes the hydrogen-hydrogen bonds to break in favor of forming nickel-hydrogen bonds. Next, gas phase ethylene is adsorbed on the nickel surface, breaking the carbon-carbon double bond in favor of forming nickel-carbon bonds. These hydrogen atoms and hydrocarbon bits are free to migrate on the nickel surface, and in so doing will collide, forming new carbon-hydrogen bonds. nickel can't hold on to the C2H6 molecules that result, so these gas phase molecules are released from the solid nickel surface. Another class of everyday catalysts are enzymes. Here we see that a crucial step in sugar metabolism requires the body to break this bond in sucrose to get the smaller molecules glucose and fructose. Unfortunately, the uncatalyzed version of this reaction is too slow to be of any use, even at the slightly elevated temperatures inside our bodies. Enter the enzyme. The substrates, or substances that an enzyme can interact with, can either fit into the enzyme's active site tightly, like a lock and key, or the substrates can induce the enzyme's active site to fit. Either way, once the substrates are in the enzyme's active site, the enzyme catalyzes the reaction. If we go back to the sucrose example, we see that the enzyme's active site puts so much strain on the bond that it easily breaks to yield glucose and fructose.